Imagine a world with no trees, no animals, no sound except the crashing of waves and the hiss of volcanoes, no oxygen in the air, no life on land, just rock and ocean and heat. This is Earth, 3.8 billion years ago. And yet, something extraordinary was about to happen. In the depths of these ancient seas, in the scalding water near volcanic vents, something tiny, impossibly tiny, was stirring. Life was about to begin. This is Earth, 3.8 billion years ago. And yet, something extraordinary was about to happen. In the depths of these ancient seas, in the scalding water near volcanic vents, something tiny, impossibly tiny, was stirring. Life was about to begin. To understand how life began, you have to understand just how hostile early Earth was. The atmosphere had almost no oxygen. It was mostly nitrogen, carbon dioxide, and methane. Ultraviolet radiation blasted the surface constantly. Temperatures were extreme. Asteroids were still pummeling the planet. By our standards, it is utterly uninhabitable. But here's the thing, chaos is also chemistry. The early oceans were a rich soup of simple chemicals: hydrogen, carbon, nitrogen, and phosphorus. Near hydrothermal vents on the ocean floor, heat and minerals constantly drove chemical reactions. And somewhere in that churning darkness, the first spark of life was kindled. The first living things on Earth were prokaryotes, single-celled organisms with no nucleus, microscopic, invisible to the naked eye. But do not underestimate them. These tiny cells could eat, reproduce, and respond to their environment. They were, in every meaningful sense of the word, alive. The earliest prokaryotes didn't need sunlight. They were chemotrophs, organisms that fed on chemical energy from the environment. They consumed hydrogen, sulfide, and iron compounds from the vents. No sunlight required, no oxygen needed. Just chemistry. Elegant, ruthless, unstoppable chemistry. And they reproduced, over and over. Simple cell division, 1 becomes 2, 2 becomes 4. Within millions of years, single-celled life had spread across the entire ocean. Every drop of seawater teeming with microscopic life. For the next billion years, this was all there was. Single cells, ruling the world. Now, if you want to see actual evidence of this ancient life, you don't need a time machine. You just need to go to Shark Bay, Australia. Here, in the shallow coastal waters, you'll find stromatolites, layered rock structures built by ancient cyanobacteria. They look like grey, lumpy boulders, unimpressive at first glance. But these are among the oldest living structures on Earth. Here's how they work. Cyanobacteria, a type of photosynthetic prokaryote, form thin, sticky mats on the seafloor. Sediment gets trapped in the mat. The bacteria grow over it. More sediment settles. More growth. Layer by layer, over thousands of years, these mats harden into rock, a biological record, a fossil diary written in stone. The oldest stromatite fossils ever found come from Western Australia, the Pilbara region. They are 3.5 billion years old. When you look at a stromatite fossil, you are looking at the remains of the oldest known life on Earth. Cyanobacteria didn't just leave behind fossils, they changed the entire planet. These tiny organisms were the first to perform oxygenic photosynthesis, using sunlight and CO2 to produce energy and releasing oxygen as a byproduct. For millions of years, oxygen slowly built up in the atmosphere. This event, called the Great Oxidation Event, would later make complex life, and eventually us, possible. Humble single-celled organisms. They terraformed an entire planet. Next time you look at the ocean, remember this: billions of years ago, in water just like this, something decided to become alive. No brain, no plan, no awareness, just chemistry that crossed a line. And everything you see, every tree, every animal, every human being, is a descendant of that first, tiny, miraculous moment.